Good afternoon, everyone. Thank you for your time. I'm Vania, and I would like to talk about my honors project under the supervisor of Dr. Arjan there. It's called Seasonal Analysis of Microhydro Energy Potential using Geographic Information System, or GIS. I hope this presentation will show how GIS can support electrification planning in a difficult and isolated areas. Maybe a little bit different from the rest of the talk today is that I would like to tell you guys about the country where I come from. I'm coming from Indonesia, and this study is actually located in Papua, and it is on the eastern part of the country. And it is shared the border with Papua New Guinea here, the Papua New Guinea here, and it's just north of the Australia. Papua is known for its mountains, dense forests, and very limited infrastructure. And because of this geographical condition, many places are extremely hard to reach, which directly affects energy access. So in Indonesia national electricity condition, electrification rate is officially 99%, which is impressive, but in Indonesia has a huge population, so even just 1% represent millions of people. And the most underserved location is in Papua, where at least from those 5 provinces in Papua, there is more than 4,000 villages that have no electricity at all. And the mountains Papua are the most severe places with more than 2,000 villages remain unelectrified. The key question is, why is it still so difficult to provide electricity to these places? So here is the example of the villages in Papua. We can see there is 2 villages that surrounded by a extremely dense forest, and it is located far from the city in those area. And the one only thing that we could reach there is just like a very small gravel road, and because of that, the transportation is very limited. And this means extending the national grid to this area needs a very long transmission line. And because of the small population, the economical benefits for building those transmission is not that great. That's why an off-grid solution like micro hydropower becomes a realistic and sustainable option. And because of most of these villages are located close to the river, I think that is a best option that we could give for those population there. And here is my proposed solution. To find a good micro hydro sites, I created a model for optimization using the run through using Python. And the process starts with locating each village's location. And then after that, from this village, we look around for the nearest river. And after that, the model searches for the best combination of water intake location, like up above there, and then also where the turbine location is. And this placement could be like a very huge amount of combination, like from like a moderate length of penstock or like a very short length of penstock. And the model here calculates a score for each possible pair, which we could look at the equation there. That is consisted of costs from penstock and cable cost construction, and also the power output of each micro hydro location. And here is the methodology that I use. The project depends heavily on GIS analysis. And first, I derive the river lines from a digital elevation model, or DEM, and then I combine them with a surface water data to get the water flow rates from for each of the points there. And then from this DEM and also the surface water data that I could get the flow rates, I could get the height difference or the elevation gradients and the flow rates of the water that are essential for calculating the hydropower potential. This GIS-based approach allows us to estimate the potential of many villages without going to the field, which is very important for remote area like Papua. And here is the example of the result for the optimization and the model itself. In total, I evaluated more than 800 small settlements across Papua. And from this analysis, I identified over 400 sites that are suitable for micro hydropower installation. This means that about half of the villages have at least one nearby river that are able to generate a useful electricity. And the other half is not that they are not having any potential location or potential site, but maybe there are some other sites that can even support multiple villages, because on the nearby river around those village, maybe that they are not having a high score. So like they are searching for another places that having more efficient sites like that. And here is the result of the potential hydropower output. The potential power output varies widely. Some locations produce only small amounts of power that's suitable for just a micro hydro system that support basic household needs. But on the left side, there is also like some location that have a very strong natural resources that can produce more than 1 megawatt, which is enough to support larger communities or multiple villages. This wide range shows that Papua has significant natural resources for hydropower, and the challenge is selecting the right sites. And here is the seasonal analysis that I did. Here is the monthly variation. Although Indonesia is a tropical country and they say that the river there is quite stable compared to maybe the 4-season country, but from this result, we know that the rainy season is also affecting the power potential output in Indonesia itself. So in Indonesia, the rainy season is from October to March. So we could see from the October until March, there is like a rise from the trend of its power potential. And then from April to September, there is like a decrease from the power output. In the dry season, the flow decreases, just like because there is lesser amount of water in a river. And understanding this seasonal pattern is important because micro hydro system must produce enough power even during the dry months. This is why the seasonal analysis is the key part of this study too. I also ran the sensitivity analysis on the ratio of the penstock to cable costs that is affecting the score of each site selection. And when the penstock is relatively cheap, more potential sites become viable. Like here from on the left side, is it like when the penstock is more expensive, it is like only like 446 sites that is identified. But when it's going to a cheaper site, like in a just the penstock to cable is like lower, we could like get like more than 500 location. And when the and because of that total of the site selection here, it's also affecting the total amount of power output that we could produce. So when the penstock is more expensive, we could just get a lesser amount of power output potential. And this means that engineering and material costs play an important role in determining which microhydro sites are practical to install. So the key findings of this project that there are more than 400 suitable locations for hydropower generation. And next is the possible total power output of more than 1.45 gigawatt for average condition. And the seasonal variation affect the potential hydropower output even it is in a tropical country, and the lower cost ratio results in more installation sites and higher power output. Thank you.
Thank you. Any questions? I've got one. It looks awesome. Is it likely to happen? What are the social barriers? Are the villages big enough to make a microhydro happen? Are there already microhydro? Would the government support it? Do you know any of that?
Okay. For what I know, the social, maybe it's more like economic condition there. I don't think if there is no like outside investor that will come through to this village, that they will have their own capabilities to build this system. And for what I know, the government itself is, I think, going there, but it's not there yet because like what I said, it is very remote areas. I think that maybe the government still doing their pilot in a more maybe an urban rather than those that have a very difficult condition area like in Papua.